I'm going to talk about how to calculate the number of stretching bands in a water molecule and how to determine whether each of those are IR or Raman active. This is our water molecule, and we know that it has a point group of C2B, and we know that using tables such as this one that we can find. I found this one in our book. There are a lot of them online, and it just allows you to calculate, or well, figure out the point group rather easily because you just follow the flow chart. So yeah. So right now what we're trying to do is to determine the number of stretching bands. So we want to know the stretching bands. And we want to know if they are IR or Raman active. So here, we know that this is a C2 because, well, we know that right here we have our main axis for it. And it goes 1, 2, so that's our C2. Then it has just like our vertical, which is our C. That's a C. Our C, Y, X axis is. So we have those right there. So in order to calculate the stretching bands, first we have to see how many of our operators, right, these are in this molecule, right? Our identity operator right here, we always have it. And it's how many of the stretches do we want to calculate. So we know that here our water molecule is like this. So we're trying to calculate the O to H ones. So we have 1, 2. So we have 2. So then our C2, for us to calculate these, we have to put on the ones that are unmoved. Unmoved when you're calculating for this. So in this case would be our C2. So if we're looking at through here and we do our rotation like this, which is 1, and we do a rotation like that, it's 2. How many of those stretches are unmoved? And as we can see here in the video, both of them, both of the hydrogens, both of the bonds moved. So 0 were left unmoved. Now, our mirror plane, because our sigma right here means like the mirror planes that the molecule has. This one right here is through X and C. So we know that this is our C. I always write that wrong way. Our C, this over here, like it goes sort of like back, is our X, and this one right here is our Y. So it would be, picture as like, I'm turning it around, but like it should remain like this. Picture like a circle going through it like that, like through the molecule. And that's our mirror plane, right? And as we're looking at this like this, so let's go back here. Imagine that there's a mirror right here, because this is the axis that we're trying to look at. Remember that this is our y-axis. This is our c-axis, and through here, like through the, like at the same place as the mirror, is our x, right? So we're looking at something like at the yellow, like it goes all around the molecule, right? I hope that's better. So you're watching these and these interchange in the reflection, right? And that's why we have a 0 right here. The vertical mirror plane, but through Y and C. So again, we have our C, and this is our Y. So here we're cutting like this. You're cutting through the molecule, through all of the elements in the molecule. So both this hydrogen in here in this band remain unmoved. So here we have a 2. Because if you see the molecule like this, right, you are not actually like reflecting anything to this side of the mirror or reflecting that to that side of the mirror. It's like the mirror just sees this image, so it doesn't move. So now we go to the actual calculation using our table over here. I'm going to move this like that. Okay, so there are 2 ways to calculate this. One is through inspection, which is just using the information that you have right here. So we know that we have an identity of 2, which means that we only have 2 of these bands that are active, right? And because this number right here is 0, we know that's going to be 1A and 1B. Now, here, through the XC1, we have 0 unmoved. And through the YC1, we have 2. We look at our character table right here. And we can see here that we have C right here, we have X right here, and we have Y right here. And we know that for XC, we don't have any moving. So we're not going to use the X. This one doesn't even have any of them, so we're not going to use that one. So our bands are A1 plus B2. That will be our reducible. Oh, reducible. Now, in order to know if it's IR or Raman active, we look right here. These 2. This is for our IR and this is for our Raman. So I like making sort of like a little table. So we're going to have like that. And it's going to be A1 plus B2. And I'm going to have IR and Raman right here. And then for each of these, if you see one of these, it means that it is active. So for A1, we do have a IR, active wavelength. And for Raman, we also have one. And then for our B2, we have one and we have one. So that will give us a total of 4 active.
So in order to be able to use the mathematical method, we first need to know what the elements of our character table are. So number 1 is always going to be our point group. Number 2 is going to represent the symmetry operations that the compounds with this point group possess. Number 3 are our irreducible representations, which we're going to be calculating with this method. Number 4 represent the characters. Number 5 are going to be our coordinates and our rotations. And number 6 are going to be the products of our coordinates. To make this a little simpler, the coordinates on number 5 are going to be what represent our IR bands, and number 6 are going to be our Raman. So to calculate our irreducible representations, we're going to be following a formula, which is going to be 1 over the total operations, which if we wanted to calculate for this character table, for example, we would have 1E, 2 C3s, and 3 mirror planes. So that would be 3, 2, 1, that would be 6 total operations. So if we wanted to use this formula, for example, that would be 1 over 6 times the sum of the number of operations for the operation that we're looking at. So we're going to be doing more examples using this formula, but like right now we just want to show you what we're going to be calculating. So that would be number of operations times the character of our reducible representation times the character of the irreducible. So our next example is going to be a compound that has both Fag and Mer isomers. So right now we're going to be explaining the Fag one, and that one has a point group of C3V. So right now we're going to be drawing our compound. We're going to draw it like this so it can be a facial isomer. So the next step is going to be calculating the reducible representations of this compound. So we know that according to its character table, we're going to be looking at the operations that it has in order to get the reducible representations. So next step is looking at the reducible representations of the compound. So we know that if we want to look for the irreducible representations, for this example, we're going to be looking at the OSCl stretches, and we know that the operations that we're looking at are going to be identity, 2 C3 rotations, and 3 mirror planes. So now we're just going to calculate which unmoved atoms, how many does it have. So here is my facial isomer, and as you can see, for the identity operation, let's say the green ones are the CLs, we can see that we have 3 of them, and in an identity operation, none of them move. So for that, we're going to have a 3, and then for a C3 rotation, we can look at it like this, and it has a C3 rotation, so that would be 1, that would be 2, and that would be the third one. So for those, we can see that all of the chlorine atoms moved. So for that, we're gonna have 0 unmoved. So now we're gonna be looking at the unmoved atoms for the symmetry plane operation. And to start, we're gonna be looking at the chlorine pointing towards us. So we're gonna be looking at that perspective so we can find our symmetry plane. So let's start with this first chlorine atom, and as we can see right now, there is a symmetry plane separating this half from this half. And if we do the same with another chlorine atom, that's going to be the same thing. And if we do that with a third chlorine atom, that's going to be the same. And I'm going to put a little picture around there so you can see that symmetry planes going and like acting. But like right now, you can see that if this chlorine were to go to that place, this one would go to that, it would end up being the same figure, right? So if this atom is the one that moves and this one moves to this place, we can see that the only chlorine atom that doesn't move is this one. So with that, we can say that there is only one unmoved atom at the symmetry operation. So now we're actually going to calculate our irreducible representations with the help of our formula and the reducible representations that we got from our previous exercise, which are the unmoved atoms for each operation. And we're first going to start by calculating the sum part of the formula. And so basically we're going to do this part for each symmetry operation. So we're going to start by opening up our brackets, and we're going to start with the first symmetry operation, which is identity. And there is one identity operation. Then the character of the reducible representation, which is the number of unmoved atoms, is 3. So we're going to calculate that times 3. And then the character of our irreducible representation is going to be plus 1. So we're going to calculate 1 times 3 times 1. Then we're going to add that same operation, we're going to do it for the next one, which is the C3 rotation. And there is 2 C3 rotations. There are 0 reducible representations for that. And it also has a +1 in the irreducible representation. Now onto the mirror plane. Those are 3 mirror planes. We have 1 reducible representation, and then we also have a +1 at our character table. So this is going to be 3. This is 0, that's canceled, and this is also going to be 3. So we add 3 plus 3, that's 6, and then we're always going to divide that by the total operations in this point group, which is 3 plus 2 plus 1, which is 6, so 6 over 6, that's 1. So moving on to the next irreducible representation, we're going to do the same thing. So we're opening up our brackets, and then same thing. We have 1 identity operation, 3 reducible representation, and another +1. Then we have 2 C3 rotations, 0 reducible, another +1 in our table. Then we have 3 rotations, 1 reducible representation, and here we have a -1. So again, this is 3, that's a 0, and this would be -3. So 3 plus -3, that's 0. So there is no irreducible representation in A2. Now on to the last one. We're going to do the same thing. We're opening up our brackets, and then there's 1 identity, there are 3 reducible, there's a +2 on our table, and then for the next one, there's 2 C3 rotations, 0 reducible reps. We have a -1 on our table now. Then we have 3 symmetry planes. There's 1 character for reducible representation, and now we have a 0 on our table. Now we add that, that's 6 plus 0 plus 0. That's 6. And we're also going to divide by 6 because that's the total number of operations in our for our point group table, and that's also going to be 1. So as we already know, the irreducible representations that we just calculated offer insight into the IR and Raman activity of the molecule. In order to determine which modes are IR active, we can just check if any of the coordinates respond to X, Y, or Z. So for example, in this one, we can see Z, X, and Y. So we know that those are going to be IR active. So then for these irreducible representations, it's just enough to cross-check with the ones that we calculated. So we know that the molecule has A1 and E. So if we already have a Z here, we can say that A1 has an IR band and E has another IR band. Now for Raman, we can just check if there is literally anything in the coordinate products, and then again it's just cross-checking with the ones that we calculated. So for A1, we can see that there is something in the quadratic functions column, so we know that there is a Raman band active there, and there is another one in the E representation, sorry. And then total we have 2 IR bands and 2 Raman bands for a FAC isomer of trichloro-trifluoroosmium 4.
Now we're gonna see how group theory can distinguish between a cis and a trans isomer. And this is based on the frequencies, because right now we're gonna look at the frequencies from the CO vibrations. So these are our COs and these are our CLs, right? So we're only gonna be looking at these 4. Here we know that this is a C2. We're gonna multiply these with the numbers that are here. When we only have 1, we're gonna assume that it's a 1 right here, and with whatever the irreducibles are. So for example, here for A1, we're gonna count how many operations we have. Here we have 4. So we're gonna have 1/4 times. So it's gonna be 1 times 1 times 4. So it's gonna give us a 4. And then 1 times 1 times 0, it's gonna give us a +0. And then 1 times 1 times 2, it's gonna give us a +2. And then 1 times 1 times 2 is gonna give us a +2. So this is gonna give us a total of 2 when we do the whole math operation. Simple math, it's gonna be easy. Now that we have our irreducible, it's gonna give us, our reducible, it's gonna give us 2a1 plus, because this is 2, plus b1 plus b2. So 1, 1. Now we want to know the IR and the Raman activity for these. So again, we're going to be using this column for the IR and this column for the Raman. For A1, we have a C right here. So we're going to say that it has 2 active. Now 2 because we have 2 right here. And then for our Raman, we also have him, so it's going to be 2. And then we're just going to keep doing it for all of them. So this is our result for the cis. I think I forgot to mention it. We were doing the cis. The cis isomer. Okay, so now we're doing the trans version, and as we can see, the molecule looks really different. And the point group of this molecule is also very different. It's D4H. I'm pretty sure someone else is going to talk about point groups and all of that. So now, using this, we can analyze, we can determine the operations that we have. So now that we have that, we can just do the math. It's really long for this one. So I will just write it over here. You just add them up like we've been doing. So I'm just going to write the answer for these. So from all of these, only 3 are part of our reducible. So it will be A1G plus B1G plus EU. And then we want to know the IR and the Raman. So we now have it like so. And then again, using our information from the table, we have 1 IR and 2 Raman bands. So when we compare it to our previous one, we had 4 IR. Because we had that 2 A1, and we had 4 Raman. For our trans, we have 1 IR and 2 Raman bands. So if we were analyzing these compounds and we wanted to differentiate between the cis and the trans, we would be able to differentiate them by the frequencies created by their bands. So we would see 4 IR bands for our cis and 1 for our trans, and then 4 Raman for our cis, and then 2 for our trans. So that's how cis and trans can be distinguished